network of local public science talks happening in bars and breweries all over the world. So if you don't actually live in Orlando, you can check out astronomyuntapped.org, and there's probably an event somewhere near you. So tonight, after our first presentation, we will have a short intermission break, and after that, we will have our second speaker of the evening. In addition to that, we'll have some free stickers and posters that as for the public, as we are a public education organization ran entirely by grad students and one postdoc at UCF, I would like to point out that any sort of donation would be greatly appreciated, as we have a donation jar up here at front for cash donations, as well as a Cash App and Venmo if you prefer. Just let me know and I can get you the information for that. And be sure to follow us on all social media to stay up to date with our future events. There will be one. There's actually 2 events in this month because this event is supposed to be our March event that got pushed back a week. So we will have another event in 3 weeks from today, actually. So keep posted for that. We should have it on social media in the next week or 2. Without further ado, I would like to introduce our first speaker of the night, who is a postdoc at the
Florida Space Institute.
Florida Space Institute, thank you. Dr. Kris, oh my goodness, let's go.
Laferriere.
Dr. Kris Laferriere is going to talk to us about water on the moon, and I'll give it over to her now.
Thank you. All right, hopefully you can all see the slides. If you at any point need to move closer, I won't be freaked out by you standing up or anything like that. So, as John said, I'm Dr. Kris Laferriere, recently doctored. Louder. I work at FSI, which is part of University of Central Florida, and today I'm going to talk about water on the moon, how there's sort of a lot, but also not a lot, and of course, because Artemis II just launched yesterday, I have to talk about Artemis as well. So the first thing we always ask is, why do we care about water on the moon? Does anyone have any guesses? For fuel? Yeah? Yeah, for rocket fuel. We also care about it for life support. Once you're on the moon, you need water to survive. And so that sort of motivates the Artemis missions in general, right? So we have Artemis II that just launched yesterday. They are officially to the moon, so they'll do a burn at about 7:49 tonight, and they'll head off to the moon. Artemis III, they're going to stay in Earth orbit, but it's sort of a practice maneuver before we go to the moon. And then Artemis IV and beyond, we're going to land humans on the moon again. And so this is just a little depiction of Artemis II. To remember, our astronauts have been in Earth orbit since yesterday. They're about to leave Earth orbit and head to the moon. They will go the farthest that humans have ever gone from Earth in space. Super exciting. Artemis IV, which if you look at old news or were paying attention for a while, we did call it Artemis III. Now it's IV, there's a little mission in between. We're going to the south pole of the moon because that's where water is, right? Water ice is going to be at the south pole. The exact landing site is not determined yet. This little yellow squares are depicting options that we have. So scientists, NASA, and across the world are currently trying to figure out where is the best place to go to look for water on the moon, but also to understand the geology of the moon. So they're looking for the most diverse geology. No earlier than 2028, like most NASA missions, probably delayed a little bit after that, but in the next few years. And they'll use one of 2 landing systems. It hasn't been picked yet which one. So the other reason we should care about water on the moon is for the science part of it. Water on the moon could tell us about processes happening across the solar system. The moon is not the only airless rocky body we have. Is it our closest neighbor and our best friend? Absolutely. But Mercury is also an airless rocky body. Asteroids are also airless rocky bodies. And so the processes that happen on the moon may also happen on those objects. So here's the tricky part. What do we mean when we say water? Scientists like to say water and mean a couple different things. Traditionally on Earth, we think about water meaning liquid water, like this beautiful lake here. And it's simple, it's 2 hydrogens and an oxygen. It's what we call molecular water. In the case of the moon, when we talk about molecular water, we're typically talking about water vapor, so water in the gas form. because liquid water on the moon, it's not happening. The conditions are not right. When you hear about water on Mercury, it's the same thing. It's molecular water or solid ice. When we talk about water on Mars, there's a chance it may be liquid, but it's pretty hard to get those conditions. Water ice, of course, not here in Florida, but where I'm from, we have plenty of. This is just an example, right? Water ice, to get it, you need structure. You need it to be in a solid form, so a single molecule, not good enough. You need a whole bunch of water molecules to make ice, and of course, the right temperature and pressures. The other really fun thing is if you ever read about water on the moon or on Mercury, a lot of the times scientists say water, but what we're talking about is hydroxyl, which is not H2O, it's OH. It's one oxygen, one hydrogen. It's water minus a hydrogen. This is where things get tricky. The moon is covered in what we call silicates. That's a type of mineral. It's a silicon atom surrounded by oxygens, and it's very easy to make it into hydroxyl by just adding a proton, aka a hydrogen. The sun is constantly outputting solar wind, which is protons. And so you can make a lot of hydroxyl, but making H2O is a lot harder. So what we find on the moon mostly is actually hydroxyl. How do we find hydroxyl, molecular water, water ice? How do we find that? We use a technique called remote sensing. All that means is we're sensing from far away. We use telescopes and satellites or spacecraft. So we've got stuff in orbit around the moon. We've also done a bunch of flybys in the moon with different instruments. And of course, we put telescopes up really high on mountains, like on Mauna Kea, and try to see through as little atmosphere as possible. We also have returned samples. The moon's the only place we've gone to and taken samples back, both with the Apollo missions and the recent Chinese missions, the Chang'e missions. The Chang'e missions also have pretty sophisticated lunar landers, so they're sitting on the moon doing observations and saying, okay, there is water here right now at this instant, whereas all of the samples are typically looking at structural water. We've never returned or found water ice on the moon with astronauts or rovers or anything like that. So evidence for hydroxyl, we see it across the moon. There's a couple of my favorite ones. SOFIA is this really cool instrument that NASA built. It's a telescope. If you haven't heard of it, it's super cool because it's in an airplane. They said, we're trying to see water on the moon, but we have to look through the water vapor in our atmosphere, so let's go above as much water vapor as we can. And so they put a telescope in an airplane. M-cubed, or the Moon Mineralogy Mapper, is how we really know about hydroxyl on the moon. We found it all across the surface. And one of the ways that we know that this isn't water vapor or water ice is because we see it at basically the equator on the moon at noontime. It's way too hot for it to be water ice. So we know that it's hydroxyl. We've also found it in samples. So this is from Chang'e 5. This is a return sample. It's called a backscatter electron image, and basically the different colors show you different types of minerals. And so in this tiny corner, it's a little fuzzy over here, but we've got a handful of minerals called pyroxene, ilmenite, plagioclase, and apatite. What matters here is that apatite has structural OH. So in its mineral form, it contains OH, which means we can detect it as hydroxyl. So anywhere there's apatite on the moon, we see evidence for OH. More exciting is, of course, where do we find molecular water? Where do we find water vapor? Many years ago, not really that many, but for the singular kid here before you were born, there was a spacecraft orbiting the moon called L-Cross. And at the end of its lifetime, we said, we want to make it useful. Let's impact the moon with it. So they took it out of orbit and just let it crash into the moon, where we expected to find maybe a deposit of water ice. And we used a different instrument called LRO, which is the Lunar Reconnaissance Orbiter, to make an observation to see, okay, what happens when you shoot this empty rocket into the ground? And if my video plays, yeah, there we go. Basically, it's just coming down. LRO is much closer to the surface, and it's just taking an observation as it goes. And what we're seeing in a second is just going to be, okay, is there a signal of water vapor here? And as we cross what's called the plume, yes, there's water vapor. And so they can figure out how much water vapor that is. It's 4% by weight. We'll get back to what that means, but just know that's not a lot. We also have the lunar exosphere. So this is just what we call the moon's atmosphere. Exosphere is also a layer of our atmosphere. It's the outermost layer. It's basically where there's so few molecules that molecules don't collide with each other. And so it's just very empty. And we've done measurements using what's called a mass spectrometer. It's basically you take a box, you keep it open, you fly through the exosphere, close your box, and then measure what's inside. And they found about 1 molecule per meter cubed of water. Again, very low. Of course, we also have samples. This one's a little bit more interesting. We've never returned a water vapor sample from the moon, but instead, what Changi 5 found was this very specific mineral from a volcanic process, which is indicative of the presence of water vapor at the time that the volcano erupted. I will not be pronouncing the name of the mineral, but if you want to, I do encourage it. One thing I did not ever get in geology was taught how to pronounce minerals, so I'm just winging it. So, okay, we've talked about water vapor, we've talked about hydroxyl. Where is the water ice? That's what we're looking for, that's what we care about. There's a couple different reasons that we can figure out where water ice should be. First off, the main thing on the moon, if there is sunlight, you are warm. If there is not sunlight, you are not. There is no atmosphere to disperse temperature. So basically, the border of where the sunlight is, we call the terminator. And if you're lit, you're pretty warm, right? We're talking 400 Kelvin, that's 260 degrees Fahrenheit. If we're to the night side or beyond, that's under 100 degrees Kelvin down to about 20 degrees, that's negative 280 Fahrenheit. That's super cold. The other thing is, unlike Earth, the moon is pretty much straight up and down, right? The Earth is tilted at about 23 degrees, so northern winter happens when we're tilted away from the sun. The moon doesn't have seasons like that. It's about a 3 degrees tilt. The other thing is, you can think about it as this. You know, in Alaska or Antarctica, you have 6 months of darkness, 6 months of daylight. You don't get that at the poles on the moon. You just are sometimes lit and sometimes not, or in places like permanently shadowed regions we find typically in craters, you never see the sun. You might see sunlight reflected off nearby surfaces, but at direct spots you will never be illuminated by the sun. And so those are places we think we should find water. So what did we do? We looked there. This is data from the early 2000s. It's this technique using neutrons. The basics of it is basically, do we see less neutrons? That means there's more hydrogen. Why would there be more hydrogen? Probably water. Not necessarily conformation, but a distribution. This is the circle is like looking up at the South Pole. All of the names on here are just crater names. Cabeus craters, it's crater, Shoemaker, they're all craters around the South Pole. And then the darker the blue is, the more likely it is that we think that there's water. The other main technique we use is radar. So it's pretty hard to see because of the sun right now, but there's a handful of speckling suggesting that there's water in some of these permanently shadowed regions. But we're not talking about a lot of water again, we're talking about 6 weight percent. That's a pretty small number. Now, the Korean Space Agency built this super awesome satellite to go orbit the moon and look in these permanently shadowed regions. Typically, you can't see in a permanently shadowed region because it's dark and we're just taking photos. We need it to be bright. But if you have very sensitive instruments, you can actually use the light that's reflected off this part to see into the shadow. So this is from ShadowCam. This is a typical lunar reconnaissance orbiter imager. And so we can see into those shadows and we can figure out, are there bright spots? Because ice is typically bright. And so they looked, and what they mostly found were fresh craters, which are bright on the moon, but not indicative of water ice. You see some color changes, but that's due to a change in slope. And then this is just for fun. You can't really see it because of the sun, but you have a boulder here, which is actually blocking the reflected light from a nearby slope, and we call that doubly shadowed. So you basically have a shadow within a shadow. And this paper came out about 2 weeks ago, and the author is my collaborator, Shuai Lee, who works out in Hawaii. He's very pro-water water ice on the moon, and this paper is very anti-significant water ice on the moon. They looked everywhere. A lot of the bright features they see in permanently shadowed regions are just craters or just tricks of the light, really. There's not very much evidence for water ice at all. Okay, what else is left? Is there a difference in the shape of the craters? If there's some massive ice deposit down low and something impacts into it, that will be different. The shape, the depth, and the diameter of a crater is defined by what material it's impacting into to some degree. So they looked, and what they found was this really exciting histogram, which says, no, there's not a difference between permanently shadowed and not permanently shadowed crater distribution sizes. So what does that mean? In general, that means not all PSRs, not all permanently shadowed regions have water ice. That does not necessarily mean that some don't have water ice. Why, again, would there be water on the moon? There's a couple reasons why we think there would be. One, we know of a bunch of processes that can form OH, right? As I said earlier, you have silicates, you impart it with protons, you get OH. Under the right conditions, you can add another hydrogen and you can make H2O. You also have volcanism on the moon. As I said earlier, you can have that mineral from volcanic processes showing that there's water vapor, right? The moon is covered in what we call mare, or lunar seas, and that is volcanic material. There's a long evidence of volcanism on the moon. You can also have impacts by comets and asteroids, which can bring water there. Asteroids, of course, don't have a lot of water, but comets have quite a bit. That's mostly what they're made out of. And you can also have dust and micrometeorites, which can form water from that OH. The main other reason why we expected there to be significant water ice on the moon is because it's on Mercury. Mercury is way hotter. Mercury is way closer to the sun. And we found all this water ice up here at its north pole. This is the same thing as on the moon, right? You're pretty much upright, so you're getting regions where they're in shadow, they never see sunlight, and nearby you're getting a lot. But the temperature swings are even worse on Mercury, right? They're 530 degrees Fahrenheit on the lit side of Mercury. So why does Mercury have ice and the moon doesn't? What we think happened is that a comet impacted Mercury relatively recently, and because it was so hot, it made it actually easier for all the water to hop itself into the cold bits and stay there, whereas on the moon, we didn't recently have a comet impact. We don't have a recent source of a ton of water. So what does this mean for Artemis, for future NASA missions? One, if we look at the entire moon, it's about hundreds of ppm, 4% by weight, whatever you want to call it. That is not a lot of water. You sum that up all together, you get about a fire truck. Just one fire truck across the moon. When we look in the permanently shadowed regions and we say 5% by weight, our best case scenario is about 10 Olympic swimming pools. Still not a lot of water. That is more than you need for one rocket of just pure liquid hydrogen, but it's still not a lot. So what that means is using the moon as a stepping off point, using the water in the south pole of the moon is going to be more difficult than we maybe thought 10, 15, 20 years ago. But that doesn't preclude us from still trying to use it. The other thing that I think leads to hope is we know how OH forms on the moon. We know how H2O forms from that OH. We can do that in the lab. We do it all the time to test these processes. We could, in theory, do that on the moon to form OH there. So, in summary, some things to take away from this. Scientists like to say water, but we don't always mean it. Sometimes we mean hydroxyl or OH, but sometimes we do also mean water ice. Not all permanently shadowed regions on the moon contain water ice. Some may in larger quantities, but right now the evidence is pointing to there's just not that much there. But it would still help us. There's still enough to help sustain human presence on the moon. With that, I will take questions.
Why do we know Mercury has water
do we know?
Why do we have
So why do we know Mercury has more water on the moon? Why do we have that confidence? One, the observations of Mercury that I showed, if I can go back to it. So this is a geometry problem. These are observations by Arecibo radar, which RIP, it's dead. Very sad about that. But you couldn't use Arecibo really to look at the south pole of the moon directly as much as you could Mercury. It's just like not at the right angle. So that's one part of it. Secondly, there is a ton of water on Mercury. These PSRs, like this is meters. What is that? 3 feet, 6 feet of pure ice. That is a really strong radar reflection. On the moon, maximum we're talking 38%, probably closer to smaller amounts. You don't see the same signature in radar. It's not as strong.
So, and I haven't watched the whole thing with Eisman, but like, do you think that this is a big part as to why they're changing the plans?
Okay. The question is, do I think this is a big part of why they're changing the plans? I don't think this is why we've added Artemis 3. I think that is for the safety and well-being of our astronauts. I do think that NASA, in its motivation and its public approach, is toning down the, we're going to use water ice on the moon, because when they were planning Artemis, you know, we thought there's tons and tons of stuff, and ShadowCam launched and all of this other data started coming out, and we were like, oh God, that's going to make it a lot harder. So the reality is, as we learn more, they have to tone down the message a little bit, but Artemis 3 is more about making sure our astronauts can safely transition from Orion to the human landing system rather than changing the plan. If they really stopped caring about it, they wouldn't go to the South Pole, but they still want to make sure how much water ice is there. One of the problems with all of these techniques is we really can't see more than a meter down. So would it suck to have to dig 3 feet down into the lunar dirt? Yeah, that would be annoying. But we can't say confidently, no, there's no water down there, there's no water ice. So.
Any more questions? If not, let's thank our speaker one more time.
Hello guys. If you guys can't hear me at any point, just yell at me and I'll try to make it louder. My name is Faulkner. I am one of the graduate students at UCF. And I am the only graduate student in the physics department that does work on planetary rings. So I thought it would be very fun and interesting if I talked about planetary rings here at Astronomy on Tap, especially since I don't think many of you have experience with anything on planetary rings except for the fact that Saturn has rings. So I'm actually going to talk about the rings of Uranus and Neptune, and this fun little topic called ring seismology, and I'll get into what all of that means later on. So the reason I decided this paper and not, and this is also, by the way, this is a overview of a paper written by the authors that I have listed there, and they, yeah. So the reason I decided to do this paper was because I really wanted to talk about Uranus and Neptune, because they're not really talked about a lot, and I think that the ice giants need some love, so we're going to keep going with that. So for my talk, I'm going to introduce Uranus and Neptune and the concept of ring seismology, if you guys aren't familiar with it, and I'm sure that the only person who knows what that is me. So then I'm going to talk very generally about the methods of analysis they use, because it's a lot of scary math and a lot of scary simulations, and we're not going to talk in depth about all of that scary stuff. And then I'm going to go over the results and then discuss why do we care about ring seismology, whatever that is. So first, the introduction to the ice giants Uranus and Neptune. Can anybody tell me one thing, besides that they're blue, that you know about Uranus and Neptune? What? Methane. Methane, yes, they do have methane in their atmospheres, and that makes them blue. Keep that tip for later, wink, nudge, underline, bold, italicized. But besides that, we basically know nothing about them because there was only one mission that ever visited them, and those missions were, one mission, which was Voyager 2, and it didn't orbit around Uranus or Neptune, it just did a flyby. So it essentially went past them and said, picture, 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 and then said, okay, bye, solar system. So that's all we got on them. So another thing you might be wondering is, why do we study Uranus and Neptune together? We study them together because they are extremely similar to one another. As one of your peers mentioned, they both have methane in their atmospheres, and that gives them their very nice blue color. And they're both in the same category as each other. They're called ice giants, not gas giants, because they do have a significant amount of ice inside of their interiors, even though we don't know that much about their interiors. But, as we may or may not be aware, this was a study that was published relatively recently that said, hey, actually Neptune is not the very nice blue color you thought it was. It looks exactly like Uranus. And so this is actually a picture of Neptune, and this is a picture of Uranus. And I'm just going to ignore that because that made me upset. No shade to the authors, but I will be using these pictures because I like these much better than those other ones. Okay, so again, what do we know about Uranus and Neptune based on the Voyager mission that visited them? So we know at least that their internal structures are different from Jupiter and Saturn. And this is a figure from a paper that went an overview about what goes on inside of the interiors of the gas giants. So we can see that this is Saturn and Jupiter, and they have sort of undifferentiated interiors, so it's not separated into layers as evenly as we expect for something like Earth or the Moon. But Uranus and Neptune do have this sort of differentiation that they believe might be going on in their interiors. And yes, italicized, bold, star, asterisk, methane, blue color, asterisk. So another interesting thing that goes on inside of Uranus and Neptune maybe is that they believe that they both have a high concentration of water inside their interiors, and this water behaves like a metal at super high pressures. And you might be like, wait a minute, how is water a metal? Well, what happens in the interiors is that it gets highly, highly ionized to the point where the water atoms are so close to each other that the electrons move within the entire fluid freely. And that is how metals conduct electricity very well. So it sort of behaves something like that inside of their interiors. But if you were to see it up closer and it wasn't blurry, this diagram actually has a lot of question marks on it because we don't have very well constrained data on what goes on inside of any of the giant planets. All we have is guesses based on what we see in their atmospheres and from the missions that went there previously. So Jupiter had Galileo and Juno right now, and then Saturn had Cassini. So we know a little bit more about them, but not so much about Uranus and Neptune. But we also know that they have rings. So Uranus's rings are over here, and these are Neptune's rings, if you've never seen a picture of them before. Uranus has a mixture of broad and diffuse rings, something like this, which essentially means you have a bunch of dusty particles in a plane. So they're kind of going out into a big area like this, kind of reminiscent of Saturn's rings. And then you also have Uranus's ringlets, which is essentially one solid object. Think of it as a thread or a string of ring material like this. Neptune's rings are actually pretty different from Uranus's rings. Neptune has very, very, very faint and diffuse rings. So there is a ring that's somewhere in the interior closer to the planet, but it's very difficult to see since there's so little particles in it. But the main two rings that we're probably going to focus on in this talk are this inner ring and this outer ring. And we can see that there are structures that are inside of these rings. See, this is all structure, that we can see at least on the visible scale. And we have little clumping going on here in Neptune's rings. So there's obviously something there that's causing these disturbances. But as of right now, we're not entirely sure what that could possibly be. And a little bit more on each of their individual ring systems. I'm going to go a little bit more into detail about that because I find it interesting. This is a wonderful picture that was taken by James Webb of Uranus. See how nice its rings are and all of the inner small moons of Uranus that you may or may not know existed. I promise they exist. They're right there. So Uranus's ring system consists of 3 broad rings, and they're given by the names of those Greek letters, which for some reason I can't remember the first one, but it's Nu and Mu in the first one. And then you also have 10 narrow ringlets that are very aptly named 654, alpha, beta, gamma, eta, delta, lambda, and epsilon. Very memorable names these rings have. And when I was mentioning before that they look like strings or thread or something like that, that is what I mean by optically thick. So it's essentially these ringlets are solid objects. That's really all you gotta think about, is that they're solid, little light can get through them, and that's it. Don't think about it anymore. Uranus also has several small moons, as you can see in this picture, and as I greatly emphasize. So there are 2 shepherd moons called Cordelia and Ophelia that shepherd Uranus's epsilon ring. And the reason they're called shepherd moons is because their gravity actually shapes the ring as they're orbiting around Uranus, and they keep the rings in line. Saturn has many shepherd satellites, so this was something that, at least once these were discovered, they were like, oh, I know this exists already in Saturn, so it could exist here too, and they found them. There are other moons between the epsilon and Nu rings. We have the Bianca and Cressida, Desdemona, Juliet, and Portia. And then between the Nu and Mu rings, we have Rosalind, Cupid, Belinda, Perdita, Puck, and Mab. And some of you guys might recognize these names. These are the names of Shakespeare characters. So Uranus's moons are named after typically female Shakespeare characters. And we know that outside the ring system are the major moons of Uranus. We have Miranda, which we can see in this picture. Then we have Ariel, Umbriel, Oberon, and Titania after that. Okay, so as I mentioned before, Neptune's rings are a little bit different, as we can see maybe from this diagram. So there are 2 broad yet extremely faint rings called the Galli and Lasso rings. And there are also 4 narrow rings, like Uranus has, called the Leverrier, Arago, Adams, and the Galatea ring. We know that Neptune has 1 major moon, and that major moon is named Triton. What's interesting about this moon, though, is that it has a very high inclination orbit, meaning that it's not in the plane of Neptune as it orbits, and it also goes retrograde around the planet. So it it revolves in the opposite direction as all the other moons do, and as Neptune rotates. And that highly suggests that Triton is a captured object from the Kuiper Belt or somewhere else in the solar system. But because of this, also, Triton really doesn't have an effect on the rings as far as we know. So I was just like, here's a mention about Triton, because I felt like he deserved it, but otherwise I'm going to ignore him. Neptune has several other small moons. Every single one of Neptune's moons actually is a tiny moon. So its second largest moon is Proteus, which is around 1/500th of Triton's mass, and it's the outermost inner moon of Neptune. And then followed by that we have Hippocamp, Larissa, Galatea, Despina, Thalassa, and Naiad, all named after watery creatures in mythology. Well, that's awesome. I just gave you guys a bunch of information. What are we going to do with this information? Aren't rings just to make a planet pretty? No. Actually, it turns out you can learn a lot about how things are going on on in a planetary system or inside of a planet by observing the rings. And the way that we were able to figure that out is by studying Saturn's rings. So there was a very famous mission that went to Saturn called Cassini. It was dedicated to studying everything about Saturn, from its rings to its satellites to its atmosphere, everything. When Cassini observed the rings, there were structures that were seen only in simulations before Cassini got there. So it was able to confirm that all these processes were going on and that there were like moons inside of the rings and all these other things. But the most interesting thing that Cassini had found was that there were resonant waves inside of the rings, so these patterns that were forming, that they couldn't identify the source of until they looked into Saturn's interior. So it turns out that there are interior processes going on inside of Saturn that are making like gravitational influences on the rings to the point where they're causing waves and structure like that, which is very cool, honestly, because now we're like, oh, okay, so like we can probe the interior of Saturn now because we know what process would make this structure. And the thing is, the authors of this paper were like, okay, we can do this for Saturn. Maybe we can do it for Uranus and Neptune. Or can we? We'll see. So, now I'm going to finally get to ring seismology. What is ring seismology? So just like the Earth and the Moon have seismic activity going on in their interiors, things that cause Earth and Moon quakes, the giant planets also have these same processes going on, but because they don't have a solid surface, it's all inside of their big atmospheres. So they're essentially gravitationally driven cycles that influence their magnetic and climate variability, and that convection of gas, dependent on the density profiles and the rotation frequency of that gas around the planet, determines what structures or what resonances can be formed in like either within the radius of the planet or outside, where it could be observed maybe at a perturbation on a moon or the rings or something like that. So, how can we analyze seismic activity in the giant planets? I just told you. So again, giant planets don't have a surface, and the best way we can look at these perturbations that are being produced by the interior is to either look at the weather patterns that are produced on the atmosphere surface, or we can see what sort of patterns are being produced in the ring system itself. So the ring particles, rings are made of several particles, and those particles are able to be influenced by a planet's gravity or a moon's gravity or anything. And that motion in the interior has a strong enough effect to move the rings that are like way outside of the radius of the planet, which is I find very interesting. I think that's awesome. But there's a problem if we come to think about Uranus and Neptune's rings as compared to Saturn's rings. Uranus and Neptune's rings are much thinner than Saturn's rings, right? So there's much more material in Saturn's rings that can be moved around compared to that of Uranus and Neptune. So the authors are going to essentially determine, based on interior models, where they line up with these thin rings. And then from that, they're going to be like, okay, I'm going to eliminate certain interior processes that I know can exist, because this structure in the rings would not exist if that was a thing. So, yeah. So, as I said before, but probably worse than this sentence says, the goal of this study, done by the authors, is to predict where resonances may occur in the rings so that they may be identified by future orbiters, pray for the Uranus orbiter and probe, and this will constrain what we know about the interiors of the ice giants, just as we had done with the gas giants. Now I'm going to go into the methods and models, but I'm going to skip all the scary math that I told the grad students before, because it's scary. It's in my nightmares. Actually, I see it in my nightmares. So the basis is that you have interior models of giant planets, and these models especially for Uranus and Neptune, they use a rigid rotating model. So what that means is that the whole planet rotates at the same time, just like Earth does. So there's no part of Earth that rotates like faster than the other part. It's a solid object. That's what we're assuming for Uranus and Neptune here. And that is not usually the case for the gas giants, but for right now we're saying let's just keep it simple, and further simplifying assumptions were made while constructing this model. They assumed that the interior was made of rock, so this interior is rock, and the outer envelope is water, surrounded by a final envelope of hydrogen. And depending on these things called gravitational harmonics, which I will get to, the known values that we have and that were put into this model were derived from Voyager 2 data. So the model was trying to be simple, but as close to reality as possible to get a best comparison for what we have thus far. So for Uranus, a bunch of different variations of this model were completed, both for Uranus and Neptune. Uranus got the most models, Neptune only got one. RIP Neptune. So Uranus had 4 custom models that varied the width of this barrier between the lower and upper layers of the atmosphere. So there was instead of it having a solid barrier, there was like a diffusion between the layers. So like it would be water, 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 and then water and hydrogen, and then pure hydrogen. Depending on the width of that layer was a different model because it would produce different structures inside of the interior in different weather patterns. Additionally, a previously tested model that assumed an adiabatic environment was used to sort of give it here's a test case scenario to make sure everything's working. And for Neptune, they only have one model for some reason, and they decided that this model will only fit the observed gravity fluctuations of Neptune's gravity field. So, normal mode frequencies. I didn't mention that. That's bad of me. So, normal mode frequencies. As I mentioned, that the gas inside of the interior of these giant planets are convecting, and convecting means they're moving in like a circular type motion based on the differences in temperature. So, depending on the amount of times those structures reach the surface, go back down, and then come back up is called a frequency. And this is essentially saying, okay, I'm going to put in the convecting cells are going to convect however many times a second. Where would that produce a perturbation outside of the rings? I hope that made sense. The frequencies that they use for Uranus and Neptune models, they were computed with each other but corrected for the rigid rotating model, and to ignore any excess things that might get complicated, like obliqueness and centrifugal forces. And the location of resonances, which are produced by the different interior motions, they were calculated manually based on rotation rate assumptions for each of the planets. I know that was very complicated. Just know it was different. Now onto the results, but with no numbers, hopefully. Oh, just kidding. Okay, so for Uranus, they predicted several different types of resonances inside of Uranus's rings. And these two resonances in particular are called vertical and Lindblad resonances. So vertical resonances are any sort of disturbance that throws ring materials up and down, and Lindblad is a resonance that produces it in and outward. So both of those were actually found and predicted to be in Uranus's 6, 5, and 4 rings. So one of those really, those ringlets, the solid ringlets I was talking about, and the alpha and beta rings. And because there was less material in the diffuse rings, we don't expect to see anything noticeable inside of those diffuse rings simply because there isn't enough material to be observable as it's being thrown around. There were resonance locations that they found in the outer rings, so this is the, I believe, epsilon ring. Don't quote me on that. But they think that any sort of disturbance in that ring is caused by the Shepherd satellites because they're much closer to them and are more likely to have gravitational influence as compared to something going on in the interior of Uranus. In terms of Neptune's rings, it was a little bit more difficult because most of Neptune's rings are very diffuse, very broad. We wouldn't be able to see literally anything if something was happening in there. So the best case scenario for Neptune was that there might be either a perturbation in one of the tiny moons and the tiny moon's orbits, or it would be in either the Adams or Lassell ring, I believe, because those are the ringlets that I mentioned previously. So resonance locations fall within the Galilee ring and two inner moons, Naiad and Thalassa. And interestingly about Naiad is that it has an extremely high inclination, as Triton does, but its orbit is prograde and not retrograde. So it's abnormal to see something like this because when a planet forms, its moons usually form in the same plane as the equator. And that's why the rings are near the equators of these planets. So this tiny moon having a high inclination suggests that there was something that happened that threw it off its original orbit. And they were speculating it could have been a past resonance with Despina, or it could have been some sort of planetary or interior oscillation thing that threw it off its orbit. And that would be something else that we could see because Neptune's rings are very faint. But that would be like another thing we could observe and theorize based on those things. Yeah, so like essentially the broadband for Neptune was that anything that cannot be explained by an orbital perturbation by a moon may be an interior resonance, which is very much like I'm going to throw spaghetti at a wall. Like that's because there's this going on. You don't know that. But more or less with Uranus and Neptune, you're looking for something that would be in the ringlets and not in the really broad rings or in a satellite. Hooray! We can detect normal modes in ice giants, right? So it's time to celebrate. We can actually eliminate some interior models of Uranus and Neptune. We know exactly what we're talking about, right? Or can we? So the only possible ways that these waves and structures can be observed inside of the ice giant's rings is to have a orbiter around them, because obviously these structures are very small in comparison to like a ground-based telescope, so or what a ground-based telescope could see. So we think that the only way we could observe these things is through sending another spacecraft to Uranus and Neptune, or just using stellar occultations, and that would work best, as I mentioned, for the ringlets and the optically thick rings. So stellar occultations, essentially you watch the rings, you watch a star go behind the rings, and you're able to collect photons, how much light from the star is coming to your detector, and that can actually resolve extremely fine-scale structure, and that's how we were able to figure out all these really meter-sized structures in Saturn's rings. So that would be like the best case scenario for Uranus and Neptune. So yeah, so essentially the authors confirmed that you could do the same method that we saw with Saturn with Uranus and Neptune, given that there's some kind of orbiter around the ice giants. And the presence of certain patterns and certain structures inside of the rings can be matched to interior models, and obviously interior models that don't produce those structures cannot be the correct interior model. And as I mentioned, like the orbiter would be the only way that you could probably detect this considering they're so far away and everything is so small and faint as compared to Saturn's rings. So So Voyager 2, as I said, was the only one that visited Uranus and Neptune. Please pray for the Uranus orbiter and probe. Please. Dance in the rain, go to church, I don't care, pray for it. Do whatever you have to. But that's all I have today, so thank you.
Do you have any questions for our speaker?
I think I confused them.
Let me bring the microphone to you.
Oh, someone has it.
I know you said that you were ignoring the scary math numbers because you gave that in the grad talk. What data do you personally work with, or was this just a research paper evaluation?
That's a good question. So this is only an evaluation of a paper that was done by someone else. Yeah. All right. So, but the things that I work with specifically is I work with data from the Cassini spacecraft, and I'm currently doing measurements or like simulated stellar occultations of Saturn's B ring. And the reason I'm doing that is because anything that's been going on inside of Saturn's B ring is unknown to us because we cannot produce it in a simulation. So I'm trying to figure out how we can make an extreme, like, I don't want to get too deep into it, but like I'm trying to make and change simulations in order to match what we see in observations. I would love to work with Voyager data, but like, you know, yeah.
Any more questions for our speaker? I have one question.
Yes.
How long are these gas giants permanently having rings, or are they transient?
That's a fantastic question, John. So, I will do each planet individually. So, I don't know how to do this because I can also talk about Saturn as well. So, interestingly enough, when Cassini was on its final orbits around Saturn, they decided to send the probe in between the planet and the rings to see if there was anything there. It looked like empty space, but they weren't sure. So when Cassini went in between the rings and Saturn, there was actually an influx of ring material falling into the planet. And what that means is that Saturn is very, very slowly losing its rings because they're getting ionized by solar wind particles, so then they follow the magnetic field. But Saturn will not always have rings, and it has not always had rings. So in terms of Uranus and Neptune, Uranus's ring system is actually extremely interesting because it is made of darker material, and that material is actually very similar to the innermost moons. And there have been analysis of the orbits of these really small innermost close moons, and it turns out that their orbits are not stable on very, very long timescales. And so the leading theory right now, which we hope to look into with like a proposal of a Uranus orbiter and probe, is that we think that the satellites around Uranus, the tiny satellites, and the ring system are actually creating and destroying each other. So the rings will become moons, and the moons will then destroy each other and create rings. And then that cycle will just repeat forever and ever and ever until the end of time, or until the sun dies. So, you know, that's what's going on for Uranus. I find that really cool. It's like, you know, like regeneration. Yeah, but in terms of Neptune, Neptune is actually going to, I think, get a bigger ring because Triton is getting too close to Neptune. So at some point, Neptune's gravity will be strong enough to tear it apart, and it will become a ring just like Saturn's ring. But that will not happen in our lifetime, so don't get your hopes up, but you know, those are the, I guess, histories and futures of the ring system.